For the next talk, we have Oscar Viyuela.
Yeah, I know it's hard. Yeah, it's hard.
Talking about driven-dissipative quantum phase transitions. Thanks.
Okay, first of all, again, let me thank the organizers. I think you guys are being pioneers now with like including these talks and discussions within like the participants. I hope like this is just the beginning and now it becomes normal or usual that in conferences we have some talks about like things related to science but not specifically science. So my name is Oscar Viyuela. I'm a postdoc in a superposition between Harvard, the group of Misha Luki and MIT, and the group of Liang Fu. And what I'm going to talk about today is not actually what I do there, right? So before I even start, and since we have this very long coffee breaks, so we can discuss a lot, I'm going to tell you about, following Juani's advice, I'm going to tell you about 3 things, which is what we can remember, that I'm not going to talk about today, but that I will be happy to talk during the coffee break. And these are things that I'm currently working on and I'm very interested in. So one of the things that I'm not going to talk about today is about using Majorana fermions to do quantum computation, right? So in system of like superconducting islands that are just have some couple to each other, and you put them on top of a topological insulator or a 2-dimensional electron gas with some spin orbit coupling, turns out that you can design topological codes like the ones that we have for spins, but now for Majoranas. So something that I'm currently working on is how to do error correction and fault tolerance and all that, but in this kind of systems. And there will be a paper in the archive probably the beginning of next week. So if you're interested about that, please do approach me. And this is something that I do with Liang Fu and Sagar Vijay at MIT. The second thing that I wanted to tell you about that I'm not going to talk about today is about doing quantum simulations using ultra-cold Rydberg atoms. So at Harvard, we have this lab where we have Rydberg atoms trapped with optical tweezers, and basically we can, just by varying the distance between the atoms, we can generate or we can tailor the interactions that we have, and actually we can simulate very interesting models in condensed matter physics and strongly correlated systems. So this is something that I'm also working on and that is super interesting. So if you like it, I can also tell you a bit more about that. And then the third thing that I'm not going to talk about is using also quantum simulation platforms to simulate interesting phases or quantum phases. So in this particular collaboration, using a system of superconducting qubits, we were able to simulate something that we worked on called the Ullmann phase, which basically is a topological phase applied to density matrices and mixed states. Okay. So again, the idea is using quantum simulators to access physics that otherwise would be hard to get. And now this is all about what I'm not going to talk about, and this is what I'm going to talk about today, which is using dissipation. So again, open quantum systems. So dissipation for us is going to be a resource to find new or novel quantum phases of matter. Okay. So this is what I'm going to talk about: how to use certain numerical methods that will allow us to explore this more exotic systems or non-equilibrium phases of matter. So this work, let me first acknowledge the people that I did this work with. So as you can see, there are many people, nearly all from different institutions, so this is hard to work because everyone's like far away from each other. But still, we managed to push this and produce some works. Basically, the first one is how to extend the mean field approach to the next easiest thing you can do, called cluster mean field. Then we use some other numerical methods called linked cluster and apply this to interesting models in many body systems subject to dissipation. So basically, like the summary of what I'm going to tell you about today is like these 3 papers. I'm not going to go too much into detail on each, but just give you the main idea. But if you're interested, please see this. Okay, so this is going to be the outline of the talk. So first of all, I want to give you some motivation of why it's interesting to study many body systems or interact in many body systems coupled to external environments. Then I will explain these 2 methods that we came up with, and I will benchmark those with basically the Heisenberg model and then the Ising model, which are like the most natural spin systems that you can work with. and then I will give you some conclusions at the end, and probably some outlook. Okay, let's start. Why do I care about many-body systems? First of all, because they are very hard to solve, and they produce like very exotic phases of matter. The idea is that what happens if you want to have some sort of non-equilibrium phase in the systems? So there are two ways to do that. So the first way, you can imagine that you have, for instance, a lattice of spins that they interact with each other, and then you quench a certain parameter in your Hamiltonian, right? For instance, it can be like a magnetic field that you've added, or whatever other parameter. And now what you do is that you focus on a subsystem, and you forget about the rest of the system. So now if you look, you probably know, if you trace this out, and you look at the state of the subsystem, and you look at the long time limit, then probably what you will find is that your system here is in a thermal state. So it's like basically the rest of the system acts as some sort of environment or thermal environment, and this thing goes just to a thermal state. There are some caveats to that, and one is if you have some, if your system is integrable, so you have some conserved quantities that do not allow for this to happen, or you have some disorder, and then you have some exotic phases called many-body localized phase. These are interesting things, but again, this is not what I'm gonna tell you about. So I'm gonna follow an alternative path, and this alternative path, it's having an interactive many-body system, and now that it's also interacting with a certain environment, okay? So in general, what you will have is that if you have here a thermal environment, just as we've seen in like the previous talks like this morning, if you have an interaction with an environment, you will generally arrive to a thermal state of your system. So now what I'm going to discuss is like what are the conditions. So for instance, if we could control very well the interaction with this environment, can we drive the system into a state such that the coherent dynamics here and the interaction with the environment compete? If you go to such a situation, then instead of arriving to a thermal state, you arrive at another steady state, which is a non-equilibrium steady state. And what we are going to do is we're going to probe the phase diagram of that non-equilibrium steady state. So that's the idea. So we have this evolution that will drive our system to a certain steady state, and then we study the phases there. So instead of looking at the ground state or Gibbs state as we do in equilibrium thermodynamics, what we do is that we evolve our system, we wait till it reaches a steady state, and now we probe the phase diagram of that steady state. So again, just to emphasize this more, we have strong interactions, some coupling to an environment, and now we have a competition between coherent dynamics, so Hamiltonian, and the incoherent processes. So what are the systems where you can expect to explore this sort of things? So let me just give you a couple of examples. So one could be, for instance, something like what we have at Harvard, the system with Rydberg atoms, where you can also engineer some dissipative channel using like ancillary states or auxiliary states of your atom. And also, like, for instance, in system with nonlinear, like with cavities, where photon loss could be a thing. This is where you may expect, for instance, to see this kind of dynamics. From the theory point of view, the way you usually describe this, I'm going to elaborate on like what was said before. You have a master equation where you have this, again, coherent dynamics, dissipative process. The coherent part can be whatever, you name it. So you may have some hopping. For instance, if this is a lattice, you may have some interaction. You may have some driving with a laser. And when it comes to the coupling to the bath, you might think about some incoherent pumping where you lose photons or you have some losses in the system, etc. So since this is a very complicated problem, and now instead of having, for instance, like just two spins, we have a huge number of spins that they interact very strongly. What we do is that we simplify the interaction with the environment. So before, in the previous talk that we saw, like people play with this non-Markovian dynamics, which are more complicated than just Markovian. But then like the system to which this environment couples is usually more like simpler. So in our case, we are going to do the opposite. Like the system interaction is very hard and complicated, and the coupling to the bath is going to be in this Born Markov approximation. So basically, weak coupling to the bath we neglect memory effects, and we neglect also fast oscillating terms. So now the equation that we have is this like this Davis or this Lindblad equation with jump operators. And even though we've made this crude approximation, this is still a very hard problem because of, again, the exponential growth of this Hilbert space. So we still need more approximate methods to study this problem. Before I introduce methods to study this problem, I also want to motivate it even further why this is interesting. So even from the critical point of view, so imagine that you want to study phases of matter and how you have phase transitions between one phase and the other, but in the presence of dissipation, then like the situation is different. I want to tell you that the situation is different from equilibrium phase transitions. Why is that? So this is the idea. Our intuition at equilibrium may fail. So the thing is that at equilibrium, we usually do some thermodynamic analysis where you have some like free energy and you try to minimize that. We know that quantum phase transitions or phase transitions are driven either by thermal fluctuations or quantum fluctuations, and long-range correlations become very important. So in this dissipative or non-equilibrium context, I just want to say that the way we approach it is not through some free energy or some thermodynamic analysis, but it's just purely dynamical. So if there's some order in the system, eventually in the ground state, it has a purely dynamical origin. So this is something that is different with respect to what we had before. And also the idea is that maybe in this case also short-range correlations can become important. And actually I'm going to show you that they are. Great, so let me now tell you what we did, okay? Which is basically introducing these two methods to approach this problem. Before that, let me tell you that there has been many methods or like ways of studying this problem, okay? So you can see like things like quantum trajectories that we were talking before, mean field, things more related to randomization groups, tensor networks, well, you name it. I mean, and this is not even exhaustive, right? So yeah, I'm sorry for the references. I can always send them to you later. But the idea is that you may ask, why do you want to propose something new if we already have like this many methods, right? So basically, our approach is the following, or the reason why we want to do it, is that some of the previous methods are good, like in order to do this, carry out this evolution, the time evolution. But if you want to get like meaningful results in an easy way, you can try to follow this approach, which basically is like, let's look for the simplest non-trivial methods beyond mean field. So we know with mean field we can do many things and explore very well the phase diagram. So now instead of using more complicated methods and work with finite sizes, let's see if there's something in between just doing like finite size scaling and like exact evolution or DMRG or things like that, and mean field, if there's something in between. So it's like the next non-trivial thing beyond that. And when I say here inspired by tradition, I mean what methods that people have used in equilibrium quantum phase transitions and or phase transitions, and see if we can learn from that. So the two methods that I'm going to explain is, the first one is called cluster mean field, which is basically the simplest generalization from mean field analysis. And the idea is that we know that mean field in low dimensions fail, and also we have no guarantee that it will even eventually succeed in equilibrium, because this idea of we don't have like this self-consistent check with like minimizing the free energy, etc. Then the second thing is that, or the second method that we proposed is called linked cluster expansions, which basically the idea is that we replace now finite size analysis by some series extrapolation. I will explain or elaborate a bit more on that. And the good thing is that we can even retrieve critical exponents beyond mean field. And then on top of this, so this is like a mask or the framework that we are going to analyze. And then for the evolution, since we want eventually to reach this steady state, we will also employ quantum trajectories, MPOs, like basically DMRG methods and quantum trajectories. Yeah. Okay, let me tell you the first one, cluster mean field. So we have, again, a master equation coherent evolution, and dissipative dynamics. The Hamiltonian that I'm going to use is the Heisenberg model. So basically interactions between nearest neighbor spins, where this sigma x, y, and z are just the Pauli matrices. And the dissipative channel is just basically what it does is just it takes like my spin up and it will just flip it down at a certain rate gamma. Okay, so basically I have the coherent evolution, and then on top of that I have some dissipative process that basically flips my spin down. So mean field applied to this problem basically is like, instead of considering this many body interacting system, I will consider that the effect of all the other spins on one single spin is just a background field, right? So I approximate that, like the effect of all these interactions that I have, just by a background field. So this is the crudest approximation that I can ever make. Yeah. If I want to do this cluster mean field, then basically it's just I will consider like I have exact interaction between a group of clusters. Like for instance, these 4 spins, they will interact exactly as my Hamiltonian said, and then the rest are considered as a background field. And then I can grow this cluster size. Like the more I can grow it, the better in general, but this is going to be limited by my numerical capacity. Great. So let me tell you what like the analysis of these methods give if you do mean field. So this is basically the phase diagram. This was computed actually a few years ago in Lukin's group, and this is just fixing one of the coupling constants, JZ, to 1, and then have some plot, like plotting against the other 2 coupling constants. So what we see is that we have some antiferromagnetic phase, a paramagnetic phase, a ferromagnetic phase, a spin density wave. So the phase diagram is quite rich. We are going to focus only on this region. And basically, we want to see the fact that we start including these short-range interactions in the system, or these short-range correlations. What's the effect on the mean field result? So basically, when we do cluster mean field, well, for the first result that we get is that this phase diagram is independent, basically, of the dimension. So in 1D, it also predicts that you have many phases. If you start using this cluster mean field, what you quickly see is that in 1D, you have no order phase, which is something that you more or less expected, since like finding temperature, for instance, you don't have like these order phases in 1D. So here you're not in that case, but also you have this dissipation, so you may expect that this is something natural. The like more interesting thing happens in 2D. So if we look at this region, basically what we had previously is that above a certain value of JY, we have always a ferromagnetic phase, and also we have this paramagnetic phase. And now what we see is that if we start considering clusters of like larger size, this ferromagnetic phase basically shrinks. But it shrinks very much. So before it used to go like to infinity. So for any value of JY, you had this ferromagnetic phase. And now just by including like these very small clusters, like the exact interaction between the small clusters, then suddenly you've reduced your ferromagnetic phase to a very small region. So we can actually see or prove that this doesn't go to 0, so it goes to a certain, so there's a ferromagnetic region, but the whole topology of the phase diagram has changed very much. And this is something that doesn't happen in equilibrium thermodynamics. So if you take cluster mean field over mean field solution, it will reshape slightly your boundaries, but it won't change dramatically like the phase boundaries as it happens here. So it seems like these short-range interactions or short-range correlations play a bigger role than they used to do for equilibrium phase transitions. And the second thing is that if we increase the dimensions, if we go to 2D lattices or 3D volumes, 4D, usually we expect that mean field tends to be a very good approximation. But what we see is that even for these very small clusters, and even at 4D, for 4D, like the ferromagnetic phase is like very, very strongly suppressed. So even if we go to like very high dimensions, like mean field is not a very good method. But also the good thing is that as soon as we include a little bit of like these short range interactions, then like you converge very quickly to the good result, to the exact result. Okay, this is the first method. Then the second method, which is called linked cluster expansions. So here, at some point, this method becomes a bit more like involved or less intuitive. So I just want to give you like the main idea. So these series expansions are used in statistical mechanics very much. For instance, if you want to analyze like, I don't know, any classical model, one thing that you can do is that at high temperature, you can always expand your partition function in terms of this beta, right? If you're at high T. Also in quantum phases or quantum Hamiltonians, you can always do this perturbation theory in which you can expand, for instance, your energy in terms of some coupling constant. This is just doing perturbation theory, right? So there are methods already that they use like perturbative or series expansions of your observables, right? So linked cluster expansions do something very similar, but it's just they rearrange the summation in a different and more clever way. So basically, this is the idea. We have this many body system where we have some coupling constants. For instance, this one is coupled with like J1, J2, J3, whatever you name it. And the idea is that any extensive property could also be expanded or expressed as a series expansion of these J's. So basically, this is as before that we had this perturbation theory, and then you can always express it as a series expansion in epsilon, right? In epsilon, epsilon square, epsilon cube. Same thing here, but now, for instance, your interaction is given by J. Yeah. So this is something that any function could be expressed this way. And now, basically, what this cluster method tells you is that you can rearrange this summation in clusters. So you, like, each cluster basically only includes J's that belong to, for instance, if this is a cluster, then the J's that will appear here would only be the one related to this bond and to this bond. The other one related to this cluster would be to this bond, to this bond, and to this bond. And by doing that, basically, you see that if like only J's related to these clusters will appear in the summation, and yeah, and that's it. And then at least when you have the cluster, for instance, if you have this bond here, at least you will have 1 power of the J according to this bond. Okay. So even if this doesn't come, and then you can simplify. You don't need to compute 1 million clusters. Basically, you can relate them by symmetry, and yeah, but you can basically relate them by symmetry, and then you need to compute only a few. So the bottom line of all this is that you can apply this method to also having Liouvilleans, right? And then the idea is that if you combine this method with perturbation theory, you can soon realize that you would only need to consider clusters of size the order of your perturbation theory. Okay, I'm not gonna get like very much into that because I would say just grasping the details there, it's harder, but that's the thing. So I can access something in the thermodynamic limit by considering a finite size clusters. That's the whole thing. So I'm not doing finite size scaling here. I'm just like gonna obtain a certain series expansion in perturbation theory, and I will replace basically finite size scaling by series analysis. So basically, this is what I wrote here. So there's only a few clusters that I will need to consider, but still the results are going to be given in the thermodynamic limit. So let me give you an example. So for instance, you can take this XXZ model, which is basically a particular case of the Heisenberg Hamiltonian, and now we add a certain perturbation on Y. And I'm not going to explain like this. I'm just going to tell you that there is again a transition, paramagnetic to ferromagnetic phase transition here, and using this method and extrapolating or doing the analysis over this series, we can obtain the critical exponent. And then when we look at the critical point, this Perret analysis is basically this method, the linked cluster expansion. It's just the series analysis. We locate it very, very close or very well with respect to other methods. So this is using this cluster mean field that I explained before, and this is another method based on randomization group. So the good thing is that, yeah, we locate this critical point very well, and also we can give these critical exponents that these other methods cannot give. So again, the method is not very complicated. It's just a rearrangement of a sum of a series expansion. But it turns out that with that, we can like give very good results, even when you compare it to more complicated or more involved methods. So then okay. Yeah, I'll be very quick. So then the final thing is that how can we benchmark this against other methods? So I'm going to tell you a particular case, which is studying the transverse field IC model, but with dissipation, and how our methods does better than other more involved methods. So again, this is a model that you could think about how to simulate it in like this Rydberg atom trap. And here I included two types of dissipation. Maybe one where I flip my spin in the z direction, and then the other one where the dissipation flips the spin in the x direction. If I take first the z direction, then what I'm going to tell you is the following. So this blue line here basically indicates a certain region in phase space where mean field theory shows B stability, that I have some sort of bistable region. Just including mean field or cluster mean field, what we show is that actually this bistability is just an artifact of mean field, and what we have is either a first order phase transition or a crossover. So here we see a crossover, here we see a first order phase transition. So there's no bistability. And just by including this cluster mean field, we can get that. Great. The second thing, if we have spins that flip it, so if dissipation flips spins along the field direction, then basically if we do mean field theory, we have a region, which is basically this one here, where we have a ferromagnetic phase. And when we start including clusters, for 2x2 clusters, it seems that this is a first order phase transition, so there is a jump. But as soon as we include more clusters, we see that the correlation length diverges, and this is just a standard second order phase transition. What happened is that if you use other more involved methods, for instance, this Keldysh formalism or variational ansatz, which are way more involved than what I presented to you, based on path integral formalism, etc. Basically, they give other results. They say that you have a first order first transition for some dissipative rate, or you have like more complicated phases that clearly we can rule out. So we observe that when we only have these 2x2 clusters, as we increase the size, we completely rule that out. So our method, it's very cool. And then just to flash the conclusions, again, we've extended these methods very well studied in classical or in equilibrium thermodynamics to the non-equilibrium context. And even though they're very simple, we've shown that they can beat way more complicated methods. So that's basically the whole message. Thank you very much.
Okay, we have time for maybe one very quick question.
So potentially very random question, but in Reaper atoms, in gold atoms, they have now long range easy models. Yeah. Can you apply your methods to long range?
That's a very good question. Yeah. This is probably the next thing that we are gonna do. Yeah, like how you can, because there you can have like not only these ferromagnetic phases, but also more complicated C2 to C3 phase transitions, and then how that goes, or how can we do that for systems that also have dissipation is not clear. Because in our experiment, basically, dissipation is not an issue, but you can basically enhance it if you want.
Okay, so maybe we have to stop here because we're running a little bit late. So let's thank Oscar again.